Okay, folks, welcome back. We're running a little late already, so I think we'll crack on. Right, packed programme this afternoon, 3 more lectures to kick off with. We have one from Neil Sugden from Transmode on how to decouple network scalability and network power consumption without sacrificing performance. So a little brief bio from Neil. Neil was educated at the University of Central Lancashire and started his telecoms career managing transport networks in the electricity supply industry in the early 90s. In 2000, Neil joined the cable industry with responsibility for core and metro optical transport architecture. He delivered market-leading architectures providing backbone integration, VOD, CMTS, and business-to-business backhaul networks. In 2007, Neil joined Transmode, where he continued to work with MSO and cable operators, where in 2011 his team was responsible for architecting the largest mobile backhaul Sync-E network in Europe for Virgin Media, delivering gigabit Ethernet backhaul from greater than 2,000 fibers, delivered cell sites for EE and MBNL. Thank you, Neil. Welcome.
Cheers. Thank you. Thanks very much, Mark, and thanks. I'll need the divot. So my name's Neil Sugden, and hopefully you've all enjoyed your lunch. I heard somebody just mention as I walked past that they want to get their head down and to give them a nudge if they start snoring. So let's try and keep it relatively interesting. So for those of you who don't know Transmode, we're an optical vendor. And we spun out of Ericsson in about 2000, so we're based over in Stockholm. I'm going to be talking about how we can continue to scale the networks of today and moving into tomorrow without having to continually increase the power consumption that's driving these networks. So, with about 1/3 of the planet now online, a 10 times increase, a 10-fold increase in bandwidth consumption over the past 2 years, and a 1,000-fold increase in the number of data centers over a similar period of time. The industry that we all work in is responsible for around about 2% of global power consumption. Now, if we add access devices onto that, so our cell phones and our tablets and PCs at home, is closer to 10% of global energy output. So it's a really significant number. It's something that we all have a responsibility to consider when we design and build networks. And when we're thinking about power consumption, we have to think about the whole life cycle of the product. So we need to think about the physical design of the hardware, make sure that we're not designing too many features that aren't needed. Very, very common today for vendors to overspecify, to future-proof the hardware that's deployed into the ground. But that drives up power consumption and unnecessarily drives up power consumption in a lot of instances. We need to think about how and where we manufacture the components. As I say, we're based out in Sweden. We do the majority of our manufacturing in Sweden. And in terms of a green manufacturing environment, Sweden's pretty green. We contribute about 40 grams of CO2 into the atmosphere for each kilowatt of power generated. If you contrast that with here in the UK and maybe the German economy, that's closer to kind of 450 grams of CO2 for each kilowatt that's produced. And contrast that further with, for example, the Chinese market. There's a huge manufacturing base, not just in our industry, but across all industries over in China. They're closer to 800 to 900 grams of CO2 that's pumped out into the atmosphere for every kilowatt of power that's generated. We also need to consider the supply chain. If you've got manufacturing across the four corners of the globe, you'll have departments that are constantly flying across those regions to manage and maintain those supply chain activities. If you have a centralized supply chain, then you're going to be reducing the carbon footprint of the operations of your business. But the most dominant facts associated with power consumption are the way that we build networks. It's the way that we build and we architect the networks, and the in-life power consumption over the 10, 15 or 20 years that the network is going to be in the ground. You know, if we consider the access networks that are in the ground today, they've been in the ground since, Alan was saying, kind of late 80s, early 90s. So they're in the ground for like sort of 20, 25 years. From an access network perspective, a metro network perspective, we tend to refresh networks about the kind of 10 to 15 year period, and core networks are refreshed on an awful lot more regular basis. So I'm going to be focusing a lot in terms of the access technology. I think we're in a position where we're going to be moving towards an access network refresh around the markets of Europe. So if we look at what's driving bandwidth, we all know what's driving bandwidth, but let's just put a little bit of context behind that. So the days of everybody sitting around the TV, those days are gone. We want content on demand. And you know, I personally, I've got 3 daughters, I've got my wife, and you know, we no longer sit down and watch TV as a family together. I don't know if that's a sad reality, or it's a more familiar reality that we're all moving towards. But it's very common that I can have my 12-year-old watching one TV streaming content, my 10-year-old streaming content, and even the 4-year-old. I was just telling a story to a couple of guys at lunchtime. She's now managed to find the BBC, the CBeebies app on my phone, and she can actually navigate to watch CBeebies by herself. So she's now familiar with the technology. So it's very common for us to be watching 2 or 3 or 4 different video streams within the house. And it's not just the content of the TV. They have second and third devices, so the watching TV and the talking to the friends or FaceTiming the friends. So if you look at the bandwidth that I'm drawing into my house, you know, it's probably, you know, 20, 30, 40 megs worth of bandwidth if we're talking about a HD stream. Now, there's a business case going through my house at the moment about a discussion for a 4K TV. It's not going well. But you know, you can see that in 3 or 4 years' time, I'm not going to have kind of 3 or 4 HD TVs. We'll have 3 or 4 4K TVs. In my mind, we will. My wife has a very different view on the matter. But just to stand still, I need 150 megs worth of capacity into my house. And if we look at where the capacity is growing disproportionately. Capacity is growing far faster in the metro network than they are growing in core networks. And I'll go into that in a little bit of detail. So this is predictable. This is predictable capacity. So this is capacity that network planning managers will see. They can see upward trends, and they can see seasonal variations. You know, through the summer. Traffic isn't too high getting towards weekends and winter when people are stuck in, capacity increases an awful lot more. So this is predictable and this can be planned for. But what can't be planned for is this young lady. What was a global phenomenon, well, it wasn't actually this young lady, it was actually this man. So this man is Mark Zuckerberg. And it wasn't actually Mark's fault. I can't remember the person that instigated the Ice Bucket Challenge. But at the back end of the summer, there was a viral event on the network. And it wasn't just a fixed network, it was a mobile and fixed phenomenon. And at the bank holiday at the back end of summer, everybody in my house got wet. And by definition, all of that content was uploaded onto my wife's Facebook page. I don't have a Facebook page myself, but it was all uploaded onto that one Facebook page, and it was automatically distributed to all of her contacts. And then all of her contacts did the same thing. It was automatically distributed to all of their contacts. So we ended up with this viral sharing phenomenon which hit the network over a very short period of time. Now this is a lot more difficult to plan for, and the end users of the network don't really care about the challenges that we have as network operators. What they care about is getting the view and the visibility of their friends getting wet, and it has to be the right quality of experience for the end customer. If we don't have the quality of experience, there are plenty of operators out there who will give that quality of experience. So if we look at the traffic distribution across the network and where that's going, so as I've just illustrated, I need at least 100 megs today in my house. So I need 100 megs across the access network just to stand still. If we consider future technologies, where are we going to be going in the future? Will we be delivering holographic TV? What's graphene going to bring to us as a technology or an application enabler? We don't know, but we need to be prepared and build capacity into the networks at the right places. Metro networks today, predominantly 10 gig going to 100 gig, and 100 gig in core networks going tomorrow towards 200 gig. So why is this happening? It's to do with the habits of the end user. So the end user no longer wants to watch that broadcast flow. He actually wants a unicast experience. So watching something over Netflix, there is a tied up bandwidth pipe from the residential home to the ingress point into the network. Now where that ingress point can vary a lot on different operators. We have certain operators which will peer with the likes of Netflix and BBC iPlayer to keep that capacity down as close to the network edge as possible. So this is why we have a higher capacity increase within the metro networks. There are other operators that won't peer with content providers like Netflix or BBC iPlayer. They will provide a transit connection at the edge of the network, and that ties up capacity across the metro network and the transit network, and the core network. For instance, you would only peer with your peers. It's a rule of thumb, and content providers most definitely are network operator peers. Also, content providers are bringing capacity onto their networks as well. So VOD services are being delivered by service providers to bring an additional revenue stream into their pocket. So we have this distribution of traffic across the network. So we need to focus towards the kind of metro and access networks. And we're also seeing that, across those metro networks, capacity needs to be flexibly distributed across those metro networks. We could be having there could be a residential estate off one node. There could be a business estate off another node. There could be a data center off another node. And we need to have flexibility within the infrastructure to be able to deliver capacity to those end users and then those end nodes flexibly. But we also need to have intelligence within the transport stream. So for example, if we have a broadcast transport stream coming in from the core network, we need to have features such as IGMP, V3, source-specific multicast. So we're not transporting that packet back up into the core network. We're going to be maintaining that capacity down in the access network. So this is why the capacity growth is more towards the metro and access parts of the network. So if we look at some of the next generation architectures, so I'm going to be discussing a couple of architectures which are probably looking 3, 4, 5 years out in a number of instances. So this is the network in a regulated environment today. So there's a number of regulated environments here within the European footprint. So if we look at the access if we look at the access network, we have multiple different technologies serving different services or delivering different services within the access network. So we've got a coax, a copper coax connection into the customer into the customer house. That's fed off a street cabinet. If we open the doors on that street cabinet, and Alan showed an awful lot more detail in terms of what's in that street cabinet, we've got primary muxes, we've got SDH muxes, we've got HFC amplifiers, we've got a whole raft of technologies that are sat in those access street cabinets, all requiring huge amounts of power and all requiring operational support and demanding a huge cost from the network operator. Elsewhere, we could be delivering mobile services and we could be delivering business Ethernet services. Those services could be delivered directly over fibre from the metro edge, or they could be delivered from an MSAN in a street cabinet. Now, if we take one step back and we look at the site, the metro edge site and the infrastructure that sits in that metro edge site, we have to have reciprocal infrastructure for each technology layer. So if we have SDH in the access network, we need to have an SDH gateway in the metro edge site, and there will be hundreds of these devices throughout the network. For delivering HFC services, we need to have CMTS delivering DTV, delivering VOD, delivering DOCSIS services, and a complex edge QAM mechanism with a raft of access lasers and forward path matrices to provide that edge connectivity to integrate those services into the HFC network. And in this example, we're looking at a multi-service operator. So there'll need to be a B2B edge router that provides connectivity for the business services. There may be another layer providing backhaul of mobile traffic. Now, all of these edge services, they all converge on a common layer, and that common layer is optical. Now, there's the technology is backhaul towards the core of the network. The services are backhaul towards the core of the network where the services are actually created at that point. And if we take a view of, a pretty high level view of the capacity that's going to be leaving a typical hub site, we're looking about 10 gigs worth of capacity from a high-speed internet perspective. DTV is around about 2.5 gigs. Voice is a very small amount of the total volume. It's 50 megs, and B2B is around 2.5 gigs. So this is a generic view of the network as it is today. Now, if we push the clock forward, 5, 6, 7 years potentially, and we're delivering optical right down into the access network. We're talking about fibre to the home. We're talking about pushing CMTS into the access network. That needs to be delivered over a common optical infrastructure, potentially DSLAMs out or MSANs out into the access network. That needs to be delivered over a common optical infrastructure. But if we take a view from a GPON or a 10 GPON perspective for delivering business Ethernet, for delivering residential services, then from an access ring perspective, we've totally simplified the technology that's sitting within the access layer. So we don't have any SDH, we don't have any PDH, we don't have any primary muxes, and we don't have any HFC. All we've got is a passive filter. So a passive filter requires no power whatsoever, and don't forget we're looking at this purely from a power perspective. So we have a zero OPEX, zero power access technology. At the metro edge site, we can now collapse the equipment that's sitting in that metro edge site. So we don't have a complex edge QAM, we don't have the CMTS anymore, we don't have any SDH muxes, and we don't have any edge routers, because that's all being condensed down into the optical node, and the edge QAM function is being pushed back in towards the core of the network. The service creation function is being pushed back into the core of the network. But the capacity, we don't really care anymore about the capacity, because we've got an optical network now. So we're delivering services purely over an optical medium. So we can deliver as many 10 gigs as we want to. We can actually deliver as many 100 gigs as we want to. We're seeing DTV as a service reducing because the video experience isn't going to be delivered over a DTV platform. It's going to be delivered as an over-the-top service, which is going to be consumed by the high-speed internet service. The voice is staying about flat, but we don't have the burden of the voice technology or the technology to deliver the voice, because the voice service is now integrated into the IP flow. So everything is moving up into the customer's internet connection, and we're just seeing a general increase on the business front. So from a power consumption perspective, the savings are really quite dramatic, because we have no active access technology. The entire access network is now being converged into an optical filter. So we've got no SDH MUX, we've got no primary MUX, and we don't have the reciprocal equipment back in at the Metro Edge site. So what are the savings? So over a 10-year period, because this equipment's going to be in the network for an awful lot longer than 10 years, but we need to look at this at a reasonable time frame. The savings are more than £300 million. But what does that equate to, in terms of CO2? That's 85 tons of CO2 per year that we're not pumping out into the atmosphere, and 280,000 cars off the road here in the UK, for example. So massive, massive savings. Now, we need more than just power consumption to make the business case work, but this is just a flavour of what we're looking at from a total cost of ownership and a power consumption perspective. So that's one architecture and that's one technology. What I'm going to do is I'm just going to touch on another architecture. So if we consider the mobile space for a moment, you may be familiar with mobile backhaul networks, you may be familiar with mobile fronthaul networks, but I'll just give you a brief overview of what's going on in the mobile space. So there's mobile fronthaul as a technology. It's being championed by China Mobile. So China Mobile, the largest mobile operator in the world, and anything that they do, the rest of the mobile community tends to look and listen, and there's a lot of traction around what the Chinese are talking about at the moment. So to understand fronthaul, we'll just briefly go over backhaul, and we'll briefly look at the mechanism and the service delivery platforms that deliver the mobile service. So we'll be reasonably familiar at the left-hand side of the drawing there. We have a mobile cell site, and at the top of the antenna we've got some remote radio heads, and at the bottom we've actually got the baseband unit which drives the remote radio head. So within that baseband unit, within that street cabinet, there'll be some transport to take the service back over the backhaul network, and there'll be some Ethernet conversion and maybe some TDM conversion going on in that box. So what's the difference between fronthaul and backhaul? So with fronthaul, what the operators are looking to do, this is a future-looking architecture, so what they're looking to do is centralise those baseband units. So they're looking to strip out the street cabinets and centralise that functionality within a central office building and create a bandwidth pool within the radio access network. And what that bandwidth pool can do is mobile operators can flexibly move bandwidth around that radio access network. So for example, if there's an event at Wembley, mobile operators can move that capacity towards that event as volumes of people start to migrate towards Wembley, and when the event's over they can move that capacity back. So that's one degree of flexibility. But the largest benefit, or there's a couple of large benefits, are you no longer have the equipment in the cell site cabinet. So with that being centralised, the handoff between cell sites is simplified, and there's no security needed out at the remote access cell site as well. The challenge that we have is because in a backhaul architecture, the connectivity between the baseband unit and the remote radio head is only it's a couple of meters, and it's digitized RF over coax. In a fronthaul architecture, we're carrying the same traffic. We're carrying digitized RF, but it's over fiber this time. So we need to be able to deliver some fairly strange interface speed. So there's two competing standards within the industry at the moment. One CPRI, one is OBASI, and they have a similar interface spread from 9.8 gigs down to 0.6. And the reason why we have these kind of strange interface speeds is because we're transporting RF. To map the RF onto optical, it doesn't map into a well-known, well-understood transport stream. So one favoured speed that the mobile guys seem to be focusing on is a single sector LTE, 20 megahertz 2x2. Now this equates to 3 gigs per sector. So if we look at a cell site, we're no longer looking at a gig backhaul. We're actually looking at 9 gig backhauls, with a typical cell site having 3 antennae on the top of it. We'll need to have 3 individual 3 gig services to deliver that type of interface. Equally, we're only looking at this from an LTE perspective. Mobile operators in Europe have also got the legacy headache that Alan was talking about earlier from a service provider perspective. So mobile operators are also looking at maintaining 3G networks and 2G networks. So potentially we could be looking at 8 or 10 wavelengths down into the cell sites. Now the challenge that we have within the optical sector is the latency that's required across this access network. So the round trip delay, excluding any processing, is between 500 to 800 microseconds. So we're talking less than 80 kilometre round trip delay. Add processing onto that, then that brings that distance down to around about kind of 30, 40 kilometres. And also the synchronization within the access network is also a challenge. When your 4G MIMO device connects into multiple different cell sites, we need to have incredibly tight synchronization. But there has to be a benefit around this, because it looks like we're pushing a lot of capacity and a lot of complexity into the network for a reasonably small benefit in terms of being able to shift capacity around the radio access network. So these aren't my figures. These are figures that have come out from China Telecom. Now China Telecom is stating that 71% of their total energy bill is spent on the base station. So if we take a view of extrapolating those figures using the cost of energy here in the UK, we can see that the total bill for China Mobile is around about £2 billion per year. If we look at the saving, 71% level of that, it equates to about £1.4 billion a year saving in energy alone. Wow, that's a big number. That's a scarily big number. And that's got the industry really quite excited about this type of technology. From a greenfield application, this is a great this is great technology. From a flexibility perspective, this is a great technology. I think where there's legacy to consider, there are other business case considerations that need to be viewed. But wouldn't you like to have, the equivalent of 1.8 million cars taken off the road here in the UK? I know that when I'm sat on the M61 on a Monday morning trying to get down into Manchester, I'd like 1.8 million fewer cars on the road myself. So if we look at both of those architectures, both of those are fairly similar but pretty different. But if we look at them from a similarity perspective, both of them are pushing a lot of capacity down towards the access network, but it has to be very simple capacity. We need to have open standards within the access network. We can't be delivering CPRI interfaces over DOCSIS infrastructure. I'm afraid it simply won't work from a latency perspective, from a synchronization perspective. So we're going to have multi-service access, and it has to be completely standard. And both of those architectures are centralizing the intelligence back into the core of the network. So capacity is moving out and simplicity is moving out towards the edge, and complexity is moving back towards the core. So if we look at some enabling technologies, so we're not ubiquitously delivering packet, but as an industry, we are converging on packet. So that packet infrastructure has to be high performance. It has to be able to deliver TDM services, and it has to be able to deliver packet services. Now, to be able to deliver TDM services, we can't have any delay, we can't have any jitter, we can't have any queuing or buffering. So we need to consider the fundamental architecture of the devices that we're putting into the network. So a regular switch with ingress buffering and egress buffering and queues ain't going to cut it when you're trying to deliver high volumes of TDM services across the network. We also need to have a great synchronization, because those TDM services, they need to derive their synchronization from a physical layer, but we also need to have some logical layer synchronization built into the platform as well. We need to be able to correct for logical sync flows or sync messaging within the packet flow. So we need to be able to cater for removing any additional sync latency that's delivered into the hardware. We need to have flexibility within the hardware to be able to interface into an Ethernet network, or we need to be able to interface into an MPLS network, or we need to be able to interface into an OTN network. So we can deliver a piece of hardware into the network at the network edge and drive a couple of 100 kilometers over an optical network if we need to, or we can just drop it into the network edge, configure the interfaces as Ethernet, and provide a low-cost access circuit into our end customers. And of course, we're in a low power discussion, it has to be low power. So in terms of the access networks, excuse me a second. So in terms of the access networks, we need to be able to provide multi-service and driving multiple different services over an access fibre network. We need to provide a shared infrastructure. We can't be delivering a service per pair of fibres. It simply won't scale. So if we push WDM down into the access network, we're increasing the fibre capacity from a single fibre strand up to potentially 80 individual wavelengths. But pushing WDM straight down into the access network drives a whole lot of complexity. At the moment, we struggle to manage thousands of wavelengths within core networks or metro networks. We need to have some intelligence within the WDM network at the edge to be able to remove some of the wavelength complexities that we have. How many times have you taken a device to deliver a service to a customer, and that interface has been taken, or that wavelength has been taken. Then you've got a truck roll, you've got a delay until you can get the correct wavelength out to that customer. And we must have an open access architecture, so we could deliver proprietary wavelength services over the top of this, so CPRI wavelength services if we wanted to, 10 gig wavelength services or 40 gig wavelength services. But the volume that we see today is in Gig E services into the access network and CPRI services into the access network. So to be able to industrialize those services, we need to remove colouring from the concept of WDM. And the way that that's done is we inject a broadband light source directly into the fibre plant. The filter, it's a glass filter. It will filter out only on one specific wavelength on one specific port. It's a piece of glass, it takes no power, and it will do this for the next 1,000 years. These things have an exceptionally long MTBF rate. So if we connect up an SFP, if we connect up a laser onto one of the interfaces, in this example onto the pink interface, we'll have that pink interface filtered out by the filter, and that will be sensed by a receive sensor within the injection locked SFP. That injection locked SFP will see it's on a pink wavelength, will lock onto that pink wavelength, and will launch back pink in the opposite direction. If we want to remove that SFP from that pink wavelength and put it back onto a different port, maybe a yellow wavelength, for example, that injection locked SFP will sense that it's on a yellow wavelength, lock onto that yellow wavelength, and launch back in the opposite direction. So it completely removes the concept of colouring from the WDM access network, and it generates a colourless WDM access network that we don't actually need to be overly concerned about in terms of the wavelength utilisation, because it doesn't matter anymore. There is no concept of wavelengths anymore. So this is a great mechanism for delivering high capacity wavelength services right down into the access network without consuming any power at all. And if we want to deliver a 100 gig wavelength, we can just take that straight over the top. So as an industry, we're very comfortable with the multi-layer model. We're very comfortable with layer 0 providing ROADM-based infrastructure with filters and amplifiers. We're very familiar with layer 1 providing wavelength services, 10 gig, 100 gig services, OTN wrap services with forward error correction. We're very familiar with carrier Ethernet services at layer 2 and MPLS services at layer 2.5. And as a transport technology, this is pretty much all we need. We don't need to be delving into layer 3. And as an industry, we've been very good at providing a best-in-breed solution to each one of these layers. So we can provide an infrastructure platform, we can provide a layer 1 transport platform, and we can provide a layer 2 transport platform and service platform. And we can put these devices into a chassis, and or multiple chassis, and they can be deployed into a rack, and that'll be consuming around about 4 kilowatts worth of power. Add air conditioning onto that, we're probably close to about 6 kilowatts worth of power out of one rack. Now 6 kilowatts worth of power, that equates, broadly speaking, to about kind of €6,000, which is actually quite a lot of money. Now, there are other ways to deliver those multiple different services. We can combine those multiple different services. So rather than provide one box per layer, they can be combined into a packet optical platform. And having that same level of services but combined into a single platform will deliver quite significant operational savings, typically 70% less space and 80% less power. So a similar service blend consuming only 500 watts worth of power, so only costing, you know, 500 euros a year compared with 6,000 euros a year on the previous model. So if we consider a typical aggregation network, so this is a pretty typical aggregation network. Throughout Europe, there's many aggregation networks, like maybe somewhere in the region of kind of 50 or 100 aggregation networks, which are very similar. So at the edge of the network, within the aggregation nodes, there's a very high number of interfaces. These interfaces are carrying proportionally quite a small amount of bandwidth, and those edge aggregation devices, they're carrying out reasonably simple VLAN manipulation, and they're taking traffic in and they're pushing traffic out onto a single interface, or maybe a protected interface across a metro network. That metro network is delivered over a photonic platform, over a packet optical platform, and there's an upstream connection into a core device. Now, the core device contrasts quite significantly with the aggregation device. So there's proportionally a lower number of interfaces, but they've got an awful lot of services associated with each interface, and there's a high amount of capacity. Now, it's very common for vendors to deliver, or for network operators to deliver this service across a single vendor's infrastructure, over a single vendor's platform. And there are reasons tend to be driven more by provisioning and operational requirements rather than power consumption requirements and pure OPEX. So if we consider two different technologies, so we're talking about, you know, a packet optical platform, and we're contrasting a packet optical platform with an edge router. So typical interface in an edge router, 100 gig. Typical interface in a packet optical platform, 100 gig, a couple of 100 gig. With an edge router, typically 128,000 queues. Packet optical platform, 8 queues. We don't need, within the aggregation network, tens of thousands of queues or hundreds of thousands of queues. You need to have queues towards the core of your network to create the service. You create a per user, per service queuing hierarchy, and that's why you need to have huge numbers of queues. You don't need to have high numbers of queues at the edge of the network. In terms of weight, an edge router, typically 8 kilos, POTS platform, around about a quarter of that. Power consumption, 400 watts, POTS platform, around about 100 watts. With an edge router, you need to have an active backplane. Within that active backplane, you'll have a fabric. You may even have 2 fabrics. They need to be powered as well. With a POTS platform, there's no need for a fabric. The fabric is, and the switching functionality is taken care of on the board and is carried out independently. And if you want to transport an edge router across the network, you need an optical platform anyway. You need to have a transponder, you need to have filters, you need to have amplifiers and ROADMs. With a POTS platform, it's integrated. It's there for free. It's inherent. It's what it does. So if we look at the
I remember that, Neil. It's there for free.
So if we look at the power consumption by function, and we'll take a packet walkthrough from kind of layer 0 up to layer 3. So the vast majority of power consumption on a functional basis is carried out by network processing. Well, at the edge of the network, we don't need to do any network processing. We don't need to have huge amounts of queues. You know, when we're talking about business Ethernet services, we're talking about low latency services. As soon as you add a queue, then you're going to queue your traffic, you're going to increase the latency on your traffic, you're going to fail your SLA. You're not going to deliver the quality of experience or the quality of service that your customer has asked for. With an edge router type of architecture, you need to have these separate physical interfaces, and you need to have separate switch matrices. You also need to provide transport and infrastructure. Now, if you contrast that with a POTS platform, this is inherent within the platform. So there is no need for huge amounts of network processing at the edge of the network. Networks are upgraded on a capacity basis rather than on a queue by queue basis. We don't need to have huge amounts of memory. So that equates to somewhere in the region of 14 million euros per year. 40 million euros over a 10-year period. But this is one network. As I say, in Europe, there's 50 or 100 networks which are close, are very similar to this. So in terms of cars off the road, it's 1.2 million cars and 3.5 million tonnes of CO2 that's just being burned. It's unnecessarily being burned because of the decisions that are being made 10 years ago around the architecture of the network, because the consideration of power and performance against functionality weren't being considered, because at the edge of the network the equipment is being over-specified. Two more slides, Mark. So if we look at the developments in terms of where we're going. So 100 gig is key in the industry and is now starting to roll out in volume. So a couple of years ago, 100 gig was provided by this OIF module, which consumed around about 70 watts worth of power. But it wasn't the 70 watts worth of power with the OIF module. It was more the 200 watts of the transponder that sat around that OIF module. So typically, 200 to 300 watts or even higher was the power consumption of 100 gig. Now today we're now shipping coherent CFPs. These consume less than 30 watts, and the transponder that sits around this, or the device that sits around this, only adds quite a small overhead onto that. So we're not consuming like 300 watts worth of power, we're consuming 75 watts of power. And the industry is moving towards a very clear path to be able to deliver far lower power interfaces going forward. And as we scale up and industrialize the delivery of hardware into the vendor community and into the service provider community, then we can draw far lower cost points. So we need to be able to decouple the current cost per bit from the 10 gig reference that I'm referencing there. And we need to have technology advances rather than just margin squeezes to be able to do this. So if we look at the design of the hardware, I bought my first 10 gig interface back in the late 90s, early 2000, and it cost me £100,000+, and I have to wind it in to a chassis, and it was bloody expensive. If we look where we are today and the developments that we've taken today, pluggability has driven us from a single interface type of architecture through to a multiple interface type of architecture. So we're now delivering 6 individual transponder functions on a single board, and these individual transponder functions, they only consume about the same power consumption as my iPhone. 5 watts per individual 10 gig transponder. Contrast that to where we were 5 or 6 years ago. It's a dramatic decrease in power consumption per port. And I put a question out to my CTO only last week, when are we going to get 100 gig that's only 5 watts per port? So that's just outside the view of our roadmap at the moment, but I'm expecting that to come through shortly. And that's it. Thank you very much indeed.